At the core of NumPy are NumPy arrays, and they are the fundamental data structure of NumPy. In this video we will cover how we can create these arrays, what kind of attributes they have, and what kind of operations we can perform with them. And so the simplest way of creating a NumPy array is using a list. So here we pass a list to the function np.array, and that returns us a NumPy array. And that's the usual way of initializing a NumPy array when we have specific values in mind, so 10 to 35. If the array that we want to initialize is supposed to have some kind of structure, then we can use NumPy's utility functions. And so by structure, I mean, for example, the normal Python range, which gives us values from 0 to the value specified, and the values are always increasing. And NumPy provides a very similar function called arange. Arange also takes a start argument, a stop argument, and a step size. Next up we have Linspace. The arguments of Linspace are very similar to arange, so we also have a start and stop argument, but then instead of a step argument we have a num argument. And this num argument specifies how many values you want to have between this range. So if we run that, we get 9 values going from -5 up until 5. And these values are evenly spaced. We can also use NumPy functions to create arrays that contain only zeros or ones. And so we can use, for example, np.zeros, and we pass it some number specifying how many zeros we want, or we use np.ones, and then we get zeros or ones. Instead of a single number, we can also pass a shape argument. And this shape argument comes as a tuple. So here we have the tuple 2, 4, 3, and that will be the shape of our array. And so when we run that, we can see we get this output here. So why does this have a shape of 2, 4, 3? The shape tells us how many elements we have in each dimension. And we go from the first dimension to the last dimension. And this is the same as going from the outer brackets to the inner brackets. So if we consider the outer brackets, so that one and that one, then we have 2 elements in these brackets. So there's 1 comma separating them. And that makes up the 2 here. And then going deeper, we go into this part here. And in this subset of the array, we have 4 elements. 1, 2, 3, 4. So that's why we have 4 here, and then going even deeper, so into these brackets here, we have 3 elements, and that's why the 3 is here. Okay, the same works for ones, and we can move on to the anatomy of arrays. And of course, NumPy arrays have a lot of attributes, but we will only touch on dtype, shape, and endim. So the dtype is something that we can specify when we create our array. And here we are simply passing this list of the values 0 to 4 to our array constructor, and we specify the dtype as an integer. And so as we expect, we get as a dtype, which stands for data type, int 64. We can also change that to float, and then we get the dtype float 64. 64 stands for how many bits we use to represent one number. If the dtype does not match the given values, NumPy will cast everything to that data type. So here we're using also the values to initialize our array, but we pass as a dtype boolean. And so even though these are all not booleans, NumPy will convert them to booleans. And so if you remember, 0 equals false and the other values equal true. If we don't specify a dtype, NumPy will convert everything to the smallest common denominator. So for example, here we're initializing our array with integers, but also with floats. And the smallest common denominator will be the float, because we can cast the integers to float, but we cannot cast the float to an integer. And so to not lose any information, here we will cast to float. Next up we have shape and endim. The shape keeps track of the shape of the array. And as we saw before, the shape defines how many elements we have in each dimension. So here we create a simple one-dimensional array with 4 values. And so the shape will tell us in the first and only dimension we have 4 values. The endim will tell us how many dimensions we have in total. And so because we're one-dimensional, we have only 1. If we move to 2 dimensions, then the shape should now contain 2 values, because we have to specify how many elements we have for both dimensions. And so we run that and we see we have 3 elements in our first dimension, so 1, 2, 3. And in each of these elements, so going deeper into the second dimension, we have 5 elements each. And to give you some more intuition, usually when people hear dimensions, they think of something like x and y and moving through a coordinate system. And so the same works here. So either we move in that dimension or that dimension. And in this dimension, we can take 3 steps. So we have 3 elements here. And going in this dimension, we can take 5 steps. Okay, so endim will be 2. And what's special now is that when we index this array, we have to specify an index for both dimensions. So normally we would just write a 1 into the squared brackets, but now that gives us not a single value, but a whole array. So in the first dimension, the second element. And so if we want to specify indices also in the second dimension, we have to pass a second value. So we can pass here, for example, a 3 also, and then we get a 4. So we first selected the second element from the first dimension, and then the fourth from the second dimension. We can also use the same syntax to override elements. So here we assign to the 4, now the 10. Okay, now going into 3 dimensions. And now you might say this looks still 2-dimensional. And that's of course true, but we have to imagine that these 2-dimensional arrays are stacked behind each other. And so we can check the shape. That will tell us now in the first dimension we have 6 elements, so that are these elements. Then in the second dimension we have 3, 1, 2, 3, and then in the fourth dimension we have again 1, 2, 3, 4. And so now moving through this array, we can imagine either we go down, up, right, or left, or we go deeper. So we could say that is the front, and going one level deeper would get us to here, and at the deepest level we have this one here. So this 2D array is at the end. We can also check the endem, and that tells us 3. And of course we can also index this 3-dimensional array, and this time we have to specify 3 indices. Okay, now to the interesting part. What can we do with these arrays? And a very basic thing is reshaping. So here we have a simple 1-dimensional array with 12 elements. And we can reshape that using this shape, so the shape 3, 4. And so here we are again specifying how many elements we want to have in the different dimensions. And if we run it, we see that going from 12 elements in one dimension, so just shape 12, we go to 3 elements in the first dimension and then 4 in the second. And this reshaping of course only works if we have the appropriate amount of elements. So because 3 times 4 equals to 12, that worked, but if we try to reshape into 3, 5, that will not work. If we're unsure about how many elements we have, but we still want to reshape, we can make use of the -1. And this will automatically set a shape value such that the operation makes sense. So here we specify 2, which means to get to 12 elements, we need here a 6, and that will automatically place that 6, as you can see here. Okay, now on to comparing arrays. This is very simple. We can just use the == sign, and that will give us a element-wise comparison. Because we're often using floats in our calculations, it can happen that our values are sometimes a little bit off. So the result of our calculation might not be exactly 2, but 2 plus this very, very small value here. And of course, we know that they're still equal, but Numpy does not know only if we use the isClose function. So instead of using the == sign, we use np.isClose. And that way we don't have to care about float calculations being a little bit inaccurate. Okay, now onto the probably most important part, the mathematical operations. And these functions are all vectorized functions. And that means the function is applied element-wise. So if you think back to lists, let's say we have the list 1, 2, 3. And if we wanted to perform some operation on this list, we either had to use a for loop or a list comprehension. And because Numpy functions are element-wise by default, we can save ourselves the for loop syntax. So here we initialize some array, and then we can just write array times 3, and it will multiply each element by 3. We can also multiply arrays together, do addition, subtraction, division, also use exponents. And we can also do matrix multiplication. For that we use the add sign. And because our array is 1-dimensional here, we're just calculating the inner product, which is the same as multiplying the same array together and then summing that up. Besides these standard functions, we also have the logarithm with a base of 2, the exponential function, and the sine, but also cosine, and the other trigonometry functions. Okay, that's it for the math functions. Next up we have aggregation functions. And these work very similar to Python's built-in aggregation functions. So we also have here a min, we have a max, and a sum. Additionally, we also have average. So we don't have to sum and then divide by the length of an array. What's special for the Numpy functions is that we can provide an axis argument. And this will tell Numpy which dimension we want to aggregate. So here we didn't specify any dimension or axis, and so it just gave us the minimum value of the whole array. But if we specify axis or a dimension as 0, then it will check in this direction which of the values is the smallest. So here 7 is the smallest, here the 0, here also 0, and here also 0. If we set axis to 1, then we check in that direction, so in the second dimension. And that gives us then 0, 0, 1. The same works for max, sum, and also average. Okay, next up, combining arrays. And the main functions here are concatenate, append, and stack. And the concatenate simply takes a sequence of arrays, which it will then concatenate. So here we're concatenating 1 to 9, that's A, and then B, 9 to 0. Very similar to that is the append. Append takes exactly 2 arrays. and then actually also uses concatenate internally. If we want to concatenate arrays in a different dimension, then we can use stack, and this will stack the two arrays together, creating a new dimension. So first we only had a one-dimensional array, now we have a two-dimensional array. Okay, now to masking. When we do masking, we index the array using not integers, but Boolean masks. So here we have a simple array from 1 to 5, and here we specify a mask as a Numpy array containing booleans for each of the values. So this true will correspond to this one here, false to this 2, and so on. And so when we then use this mask to index our array, it will only give us those elements where the mask corresponded to true. So we got the 1 because we have a true in here, we also got the 3 because we have a true in here, and also the 5. And of course, defining this mask manually is not the most common use case. Usually we make comparisons like array is smaller than 5, and that gives us then our mask. So this will check which of the elements is smaller than 5, that is stored as booleans. So we get only the elements that are smaller than 5, or we could also only get the elements that are smaller than 3. Okay, finally indexing. And we already saw how we can index two dimensions. So the first value corresponded to the first dimension and the second value to the second dimension. Instead of picking only single values out of an array, we can also specify that we want all elements from that dimension. So this syntax here means we want all elements from the first dimension. So first we just select everything, but then here we say we only want the third element from the second dimension. So that will refer to this column here. And then as we see, we get this column. We can also use slicing instead of specifying single value indices. So here we take the second element from the first dimension, and then from that we take the values from the third spot up until but excluding the seventh spot. So that gives us this here. For the slices we can also specify a step size, and it's important to not mess up the order, so we don't go start, step size, then stop, but we go start, stop, and at the end we specify the step size. So this is very similar to a range or a range.